Hi, I want to explain a couple things about how frequencies arise on strings that are loaded with different tensions and with different lengths. So we can imagine here we've got one string that's pegged between two posts. There's a post there and a post there, and it's strung at some tension. And what we're going to talk about is the different frequencies that we can excite the string at when we pluck it. So the first frequency, the one that occurs at the lowest energy, will be called F1. That is the fundamental. And then these are the other frequencies. So this is sometimes called the first harmonic, the second harmonic, the third harmonic. So these are multiples of the first frequency. So what are the different frequencies that we could get? Well, you can imagine that what's got to happen in this type of situation is something where we have a vibration that looks roughly like this. So the string, because it's attached at the end here, it must stay put at that spot, and it must stay put at this spot there. So one of the things that can happen is the string can basically vibrate in the middle, but not at the ends. And so I get something like that. Now, if you pluck it a little bit harder, you get something that looks like this. As you can imagine, I've also done demonstrations of this in class, where you can get something like two lobes like that. So that's the second frequency. That takes a little bit more energy. And then you get something like this. If you go to the third energy, roughly speaking, it looks like this. So it's oscillating here, and oscillating here. And each of these is progressively higher energy. So we have a picture that looks like that, a little bit more cleanly. Now, how do we figure out what these energies are, or what these frequencies are? We want to know what these different frequencies are. The way we figure out that is by looking at what fraction of a wavelength, so this is one fraction of a wavelength that fits in this length here. So imagine that we've said that this particular thing has a length of L. So from one peg to the other, that's a length of L. Now, in this first case, what we have is basically half a wavelength that's fitting in. So this is not a full wavelength. Full wavelength would be all the way, going off like that. We've only got half wavelength here. Here we actually do have a full wavelength. It's going through a complete cycle. It starts out, it goes all the way up, it goes down again, and it comes back. So that's a complete wavelength. And here we have more than one wavelength. We have 1.5 wavelengths, or 3 halves of a wavelength. So we use that information and the number of wavelengths, or half wavelengths, and we relate it to L. So we can use that to solve for the frequency. Let me show you in the next part here. So let's go over the first case. As I said before, this is just half a wavelength that's fitting in here. Remember, a whole wavelength is one lobe up and then one lobe down. So this is only half a wavelength. So half a wavelength equals the full length of the string. If I multiply both sides by 2, I get that the wavelength in this case is equal to twice the length of the string. I can do that for this. Here I have one complete wavelength, and that actually equals the length of the string. So here, the wavelength equals L. But here in this situation, what I have is I have one wavelength plus another half. So I've got 3 halves of a wavelength. So 1 half, 2 halves, then 3 halves. 3 halves of a wavelength equals L. And if I solve that for the wavelength, I multiply both sides by 2 and divide both sides by 3, and I get the wavelength equals 2/3 of L, right, like that. So now I've got these different expressions for what the wavelength is in these different cases. So if I know the wavelength in each case, and I know the velocity on the string, I can basically get the frequencies. So let's see how we do that. Remember this relationship. We say frequency times wavelength equals velocity. So I can solve for the frequency, and that's just going to be the velocity divided by the wavelength. Now what I can do is I can plug in the different values of wavelength that I got on the previous page, and I can solve for the different frequencies. So go back here. Remember, the first frequency, the first harmonic, the fundamental, we've got half a wavelength equals L, which means that the wavelength equals 2 times L. So I'm going to go into this equation here, and I'm just going to plug in for this, for lambda, for the wavelength, I'm going to plug in 2 times L. So the first frequency is just V divided by 2L. Let's just look at that. Don't worry about this stuff over here yet. So just worry about this. All I did was I plugged in the value of lambda that I got in the previous page. Let's go for the second frequency. So for the second frequency, what I have here is a full wavelength equals the length of the string, so lambda equals L. So when I get to this formula, instead of plugging in lambda, I'm going to plug in L. So down here, F2 is equal to the velocity of the wave on the string divided by L. So that's good. I just get that. No problems with that. Don't look at this stuff over here yet. Now in the third case, when we solve for it, remember what we got was that the wavelength equals 2L over 3. So when I get to this equation here, I just want to put in something for L, for lambda, okay, and this is going to be 2L over 3, so it looks like this. Here's my equation. I plug it in. This is the velocity of the wave on the string, right there, and here is just what we previously solved for lambda. I plug that in, and dividing by a fraction is the same as multiplying by its reciprocal. So I put the 3 up top, and I put the 2L down below, and I get this. Now you can look at these equations here, and you can see a pattern. What I have is, it's always some number of v, so it's 1v, or 2v, or 3v, but it's always divided by 2L. So that leads to this formula that the nth harmonic is going to equal to n times v, all divided by 2L, where n is equal to 1, 2, 3, etc., like that. So that's the formula to give you the different harmonics of the string that's fastened at both ends. And remember that the lowest energy is going to be n equals 1, then slightly higher is n equals 2, and slightly higher is n equals 3. You got that. Now, the other key thing to remember is that the velocity that we're talking about in this formula is not the velocity of the sound going through the air. It's the velocity of the sound traveling on the wave. So if I have or sound traveling on the string, so it's the velocity of the string wave. So we went over this before in class, but just to remind you of it, and we give you this formula on the exam, the velocity of a wave on a string is given by the square root of the tension divided by the mass per unit length. Mass per unit length is mu. So this is mu. It's just the mass of the whole string divided by the length of the whole string. So that's the V that you need in this formula up here. That's the V that you're looking for a string. And don't confuse that with the velocity of sound in the air, which is like 343 meters per second. All right, so let's do an example problem. What is the fifth harmonic of a 1.5 meter long string that has a mass of 3 grams and it's under a tension of 10 newtons? What would be the fifth harmonic? Well, to do that, what we're going to do is we're going to look at this kind of formula here, and we're going to plug in n equals 5. So the fifth harmonic, we're going to have 5 there. We're going to need to calculate the velocity. We need to know the length of the string. All right, so let's get to it. What's the fifth harmonic? So we're going to get the velocity of the string. We're told something about its tension. Its tension is 10 newtons, so it's under 10 newtons. Its mass per unit length it's 3 grams, and its length is 1.5 meters. But remember, grams is not an MKS unit, meters, kilograms, seconds. So all of our units work out well if we have them in meters, kilograms, and seconds. So I got to convert 3 grams to kilograms. All right, so there's 1,000 grams in 1 kilogram. So this number right here is actually 1, but it's got different units, and this allows me to cancel grams with grams. So 3 divided by 1,000, and now divided by 1.5, that's the number down here. Plug all these guys into the calculator, and what I get is the velocity of the wave on the string is 70.7 meters per second. That's the velocity you want to plug in here in this equation. This is the fifth harmonic, so it's F5. So I put a 5 there, put in the velocity of the wave on the string, and then I put 2 times the length of the string. So I plug that in, and basically I get a frequency. So meters cancel with meters, I get 1 over seconds, which is hertz. So 117.8 hertz. That's the frequency of this particular string. So just to summarize, what we've talked about is how you can get different types of modes or frequencies or harmonics on a string that's pegged on both ends. And using this setup, we can calculate what the wavelength is relative to the length of the string, and from that we can get the different frequencies. And then we remember that the velocity of the wave on the string is given by square root of tension over the mass per unit length. Hope that